Welcome to this explainer on Chapter 1 of Database Systems. I'm really excited to guide you through this material today. Whether you're aiming to be a front-end developer, a back-end architect, or a data scientist, setting the stage for why database mastery is essential is arguably the most important step in your entire software engineering program. A great full-stack developer must first be a great database designer. It's absolutely crucial. So today, we're going to build that foundation together.
Here's a quick look at the 6 core sections we'll be covering today. Data versus information, introducing the DBMS, types of modern databases, the file system nightmare, redundancy and data anomalies, and finally, the environment and exam summary.
Section 1. Data versus information, from raw facts to knowledge.
Okay, before we even think about building complex systems, we have to understand our foundational raw materials. Now, in software engineering, you'll often hear people use the words data and information interchangeably, but strictly speaking, they are very different things, and it's a common misconception that they're the same. Here's the progression you need to memorize. First, data. Data consists of raw, unprocessed facts. The key word there is raw, meaning these facts haven't been processed to actually mean anything to the end user yet. Next, we have information. Information is the result of processing that raw data to reveal its meaning. And to reveal meaning, information requires context. Finally, we step up to knowledge. Knowledge is derived from information. It implies a familiarity, an awareness, and an understanding of that information as it applies to an environment, which allows us to make key business decisions. So think of it like this. Data is the foundation of information, and information is the bedrock of knowledge.
Let's look at an example that brilliantly illustrates how we capture those initial facts. Imagine a university tracking data on its faculty members. To get data into the system, you'd provide a data entry screen, kind of like this one here from Sedona Systems. Notice the drop-down lists, the combo boxes, and the text fields. When a user is typing in a name, a department, or a rank, what they are inputting right there is raw data. Once you hit save on that entry, it gets placed into the underlying system, ultimately giving us hundreds, maybe thousands of rows of raw data. Now, while this is completely factual and accurate, let's be honest, it's not particularly useful in this format. If you need to make an immediate business decision, reading through hundreds of rows of faculty names and departments just doesn't give you much insight into the overall makeup of your staff.
But let's move to the next step and see how this builds into information. By processing that raw data, we can transform it into a summary. Suddenly, we have context. We can now clearly see the percentage of adjunct faculty in a specific department, which in this case happens to be 20%. We've successfully transformed raw facts into meaningful information.
And graphics can further enhance this context. A simple pie chart makes it incredibly easy to quickly extract meaning. This graphical information can now be handed right over to accrediting bodies to make high-level decisions about the university. So just to recap this vital section, data constitutes our building blocks, processing that data produces information, and accurate, timely information is the absolute key to good decision-making and organizational survival.
Section 2. Introducing the DBMS, the modern solution.
Now that we know what data is, we need to talk about the modern solution that handles it all, the database management system. A big trap some students fall into is thinking a database is just a glorified spreadsheet. It is not. It's a shared, integrated computer structure housing a collection of related data. Crucially, it houses 2 specific types of data. First, end-user data, which are the raw facts we just discussed. Second, metadata. Metadata is literally just data about data. It describes the characteristics of the data and the set of relationships linking the data within the database. Think of the database as a highly organized electronic filing cabinet. The Database Management System, or DBMS, is the intermediary software program that manages this cabinet structure and controls all access to the data stored inside it.
Section 3. Types of modern databases. Choosing the right tool.
With the DBMS defined, it's really important to recognize that not all databases do the same job. We categorize them based on how they're used and the time sensitivity of the information. This is a massive exam focus, so definitely pay close attention here. We generally divide databases into 2 main usage categories. First up, we have operational databases, also known as online transaction processing, or OLTP databases. These are designed primarily to support a company's day-to-day operations. They handle fast, immediate transactions, like processing a product sale at checkout or supply purchase. On the flip side, we have analytical databases. These focus on storing historical data and business metrics, and they're used exclusively for tactical or strategic decision-making. They often include a data warehouse and an online analytical processing, or OLAP, front end to massage and analyze vast amounts of historical business intelligence.
Interestingly, modern technology has radically shifted this landscape. Think about the explosion of social media. Platforms like Facebook and Twitter process petabytes of unstructured and semi-structured data every single day. Traditional systems can get completely overwhelmed by this. This immense volume, variety, and velocity of data actually drove the creation of XML databases and a whole new generation of systems known as NoSQL, which stands for Not Only SQL. These are specifically geared toward handling massive distributed data architectures. So just remember, OLTP for daily operations, OLAP for historical analysis, and NoSQL for massive unstructured data.
Section 4. The File System Nightmare. A History Lesson.
To truly appreciate the elegance of a modern DBMS, we need to jump into a quick time machine. We're going to look at the highly flawed file systems of the past. Long before databases, businesses relied on manual, paper-based filing cabinets. When computers finally arrived, businesses basically just digitized that manual system. They created computerized file systems, where every single department, like HR, sales, and accounting, created and owned their own independent, disconnected digital files. They essentially operated in total isolation, writing their own separate data management programs completely from scratch.
As you can imagine, these early file systems had fatal flaws. You must clearly distinguish between these two flaws to minimize exam confusion. First is structural dependence. This means that access to a file is entirely dependent on its structure. So, if you simply added a new date of birth field to a customer file, you would break every single application program that accessed that file. They would all have to be completely rewritten. Second is data dependence. This happens when changing the data characteristics, for example, changing a field type from an integer to a decimal, breaks the program. Thankfully, a modern DBMS provides both structural and data independence, shielding the programmer from these absolute nightmares.
Section 5. Redundancy and Data Anomalies. The Fatal Flaws.
Now, the flaws of the old file system didn't just frustrate programmers, they directly damaged the business data itself, leading to redundancy and dangerous data anomalies. Because every department managed its own files, the whole organizational structure essentially promoted storing the exact same basic data in different locations. Database professionals call these scattered, disconnected data locations islands of information. And having these islands inevitably produces data redundancy, which exists when the same data is stored unnecessarily in different places. Think about it. If the sales department and the accounting department both keep a separate list of the exact same customers, that data is redundant. And redundant data leads to our next massive problem.
Data redundancy yields inconsistent behavior, which we call data anomalies. Let's walk step by step through real-world examples of the big three. First, an update anomaly. This happens when you need to change data, like a sales agent's phone number, but because it's stored in 50 different customer files, you update it in one place and totally forget to update it in another, leaving you with conflicting information. Next, an insertion anomaly. This occurs when you literally cannot add new data because of the system structure. For instance, you hire a new agent, but the system won't let you save their record until they actually have a customer assigned to them. Finally, a deletion anomaly. This is when deleting one piece of data unintentionally wipes out another. Imagine deleting a customer record, and because that was the only place the assigned agent's details were saved, you accidentally wipe out the only record of that agent's entire existence. To wrap up this section, redundancy breeds inconsistency, and inconsistency corrupts your entire system.
Section 6. Environment and Exam Summary. Pulling it all together.
We've covered a lot of ground today. Let's pull it all together by looking at the broader database environment before we dive into a comprehensive exam review to really prioritize your study time. A fully functioning information system is far more than just the underlying software. It actually requires 5 components to work. Hardware, which is the physical machines. Software, meaning the operating system, the DBMS, and application programs. People, including database administrators, designers, and everyday end users. Procedures, which are the rules and instructions governing the design and use of the system, and of course, the data itself.
Okay, let's review the absolute must-know concepts and definitions from today that are highly likely to appear in your tests. First, remember that context is what transforms raw data facts into meaningful information. Second, memorize that metadata is simply data about data. Third, be able to contrast an operational OLTP database used for fast daily transactions against an analytical OLAP database used for historical decision-making. And finally, understand that the islands of information found in old file systems caused data redundancy, which directly led to update, insertion, and deletion anomalies. As we wrap up this explainer, I want to leave you with a powerful thought. A poorly designed database will generate bad information, which leads to bad decisions, which can ultimately lead to the failure of an entire organization. Poor database design is often the root cause of failing applications. So a great full-stack developer must first be a great database designer. As we move forward in this program into actual database creation, I want you to ask yourself, how will you design your first system to ensure your applications succeed rather than fail? Thanks for joining me for this lecture, and I can't wait to see you master the art of database design.